Hello students, this is Mr. Downing. We're going to start talking about Newton's laws of motion. Sir Isaac Newton, he contributes a lot of information to us in physics. That's why most high school classes are called Newtonian physics. Very influential fellow. He observes what's called his 3 laws of motion. He does a lot of stuff. He records them in his work De Principia Mathematica. The first, Newton's first law, sometimes called the law of inertia. It states, and obviously this is translated, an object at rest stays at rest, and an object in motion stays in motion, the same speed in the same direction, unless acted upon by an outside force. What this really says is that an object at rest stays at rest, and an object in motion stays in motion, the same speed in the same direction. This here, speed and direction, that should look familiar to you as velocity. Speed and direction is velocity. Now what they're saying is, it stays at rest or stays in motion. That means it does not change. Unless acted upon by an outside force. So velocity does not change if there are not forces. Another way of thinking that is a change in velocity is our definition for acceleration. Okay? So we'll have acceleration if we have a force. So I'm trying to say is that forces cause accelerations. This is an extremely important idea. So this is called the law of inertia. Sir Isaac Newton didn't just put all these things down in words, he made some of the words. Because a long time ago, we didn't know what we knew today. We didn't know that objects that are made out of, things that have mass are made out of smaller things, that all the things around us are made out of molecules, and those things are made out of atoms, and those atoms are made out of protons and neutrons and electrons, and that those protons and neutrons and electrons are made out of quarks. But this idea of mass, of stuff, it was difficult to wrap our heads around for a while. So inertia is how we thought of things before. The tendency of an object to continue doing what it is already doing. So what you and I would call an object that has a lot of mass, it's hard for us to accelerate it. It's hard for us to push it and change its motion. Whereas something that's smaller is easier. So a moving object wants to keep moving. A stationary object wants to stay still. Now remember this want. When we say want, we're really meaning that follows the laws of physics. We're personifying these a little bit. So let's go through some examples. So when your car stops suddenly, you keep going because of inertia. You are an object in motion, and an object in motion stays in motion. The same speed, the same direction, unless acted upon by an unopposed force. So you'd stay in motion until either the seatbelt stops you, or lacking that, the windshield. That would be that outside force. Now, inertia is only based on mass. Nothing else will influence our inertia. There's an 18-wheeler truck stopped at a light. It's harder to keep going than a little VW bug, because the truck has more inertia because it has more mass. More mass means more inertia. If they were both put into neutral, we could push on the VW bug, and we might not be able to accelerate it very fast, but would be able to get it moving. If we were to push on that 18-wheeler, we would not be able to get enough force to overcome its inertia. That object at rest would stay at rest. And it doesn't matter if they're moving either. This 18-wheeler driving 60 miles per hour is still harder to get stopped than a little VW bug going 60 miles per hour. The truck has more inertia because it has more mass. And it doesn't even matter if that 18-wheeler is going, so if this 18-wheeler was going 1 meters per second, and instead of this VW bug, let's even say it's a sports car, and it's going 80 meters per second. It would still be easier to accelerate this VW bug, or the sports car, up to 81, than it would be to accelerate this 18-wheeler up to 2. Or, it would still be more difficult to stop the 18-wheeler. By stop, I mean subtract 1 from 1 to 0 than it would be to take our sports car or VW Bug from 80 down to 79. Because the 18-wheeler has more mass, and it's only mass, not velocity, that influences how much inertia we have. So the convertible is an object in motion. An object in motion remains in motion, the same speed in the same direction unless acted upon by unopposed force. So he'd keep going until he hits this brick wall. This brick wall would be that outside force. Now if this guy does not have on his seatbelt, even after the car has that outside force, he'll be an object in motion, and he'll keep going at the same speed in the same direction until he's acted upon by an outside force, namely in this case the concrete on his face. So Halley's Comet comes by around every 76 years, named by Edmund Halley. We had a satellite the last time it came. If our satellite, if we were able to match it at the exact same speed in the exact same direction as Halley's Comet, the comet would never outrun our satellite. Even though our satellite wouldn't have engines on, the comet wouldn't have engines on it. There's no rockets pushing them. They don't need anything. Their velocities will stay the same. They will not be accelerated until there's some kind of outside force, until they eventually run into something. We've observed Halley's Comet since about 200 BC, and it hasn't hit anything yet. If we could get our satellite the exact same speed in the exact same direction, so it's not a little fast, not a little slow, not a little to the right, not a little to the left, it will be an object in motion. It will stay the same speed, same direction, unless acted by unopposed force. It will be able to keep up with the comet. The reason that things like this work in these scenarios is because there's no air in space, so we don't have any friction. This was commonly confused for a long time. It took a long time to postulate Newton's laws because things don't keep going on Earth because there's always something pushing against it, like air or the road or grass. We always rub against something, and that friction is that outside force that's slowing us down. So if a truck has a load of lumber, tailgate down, stopped at a red light, light turns green, steps on the gas hard. That truck was an object at rest. An object at rest stays at rest unless acted upon by an outside force, in this case the engine. Now the lumber, it's also an object at rest. And an object at rest stays at rest unless acted upon by an outside force. So if the tailgate's down, not to push on it, unless it's strapped down or unless there's a lot of friction with the bottom of the bed, then without enough outside force, that load of lumber will stay at rest and the truck will literally drive out from underneath it. This is a common trick. The difference between magic and physics is simply a physicist will tell you how it works. The magician will not. So whenever a magician shows you a table with a tablecloth on it, there's dishes, there's the whole candlesticks and wine glasses and silverware and plates and all that all set up. Swiftly yanks out the tablecloth, comes off the table, the dishes stay there. Now there is a slight trick to this. The only trick is that he doesn't use lightweight stuff. You use dishes and candlesticks and silverware that has a lot of mass, because having a lot of mass means it has a lot of inertia. And when you have a lot of inertia, that means there's a tendency to keep doing the same thing. They're objects at rest, they stay at rest. And so you use a really slick tablecloth, you give it a quick pull, that way you have as little friction as possible. And little friction means it's just a tiny force, not enough to overcome the inertia of those dishes. And this whole law of inertia, that's what we call Newton's first law. An object at rest stays at rest, and an object in motion remains in motion at the same speed in the same direction unless acted upon by an outside force.